Assalamu alaikum. Welcome back after the break. So Dr. Andrea will resume his talk about coloring and labeling of graphs. She is from Technical University from Slovakia. So please welcome her.
So good morning again. I hope that you are not bored, but don't worry, this is my laptop. Okay, so my last lecture is dedicated to the irregular labelings. Okay, so I will start with some background. I will go very slowly, and then I prepared a lot of material. Then I will send you a PDF file. I will send it to Prof and he will distribute to you. So I am sure that we will be not able to go through all variations of this type of labeling, but you can find here in the room several experts dealing with irregular labeling, so you can contact them if one is there. Also, you are dealing. Some people here are already dealing with irregular labelings, and they know more about this topic. Maybe they know more than me, so you can contact also them. So let's start. Yep. So I will tell you something about irregular assignment. Then I will tell you something about some variations. So it will be total labelings, then the reflexive labelings. Oh, then I have the typo, and the distance irregular labelings. So let's start with some simple problem. Okay. So we start with some basics from graph theory, basic course of graph theory. So the problem is the following. Construct a graph on n vertices whose every vertex has the same degree, say r. So do you know how to solve this problem? This is really easy. So my question is it possible to find such a graph for any number r and any number n and r for any couple? Surely no. There are some restrictions, okay? So what we would like to obtain is a regular graph, or we say it's a regular graph. Trivially, if we consider only simple graph, so we do not allow multiple edges and rules. So the degree r must be bounded from below by 0. So if we have a 0, so we will have totally disconnected graph, so just isolated vertices and isolated vertices. And the upper bound for parameter r is n-1, because one vertex can be connected to a small n-1 vertex. So this is one condition that must be satisfied. Okay? And the second one is also very known, that if we consider, or if our r, the degree of every vertex must be odd, then trivially it is known that the number of vertices must be equal. Okay, but otherwise, to construct such a graph, regular graph, is not complicated. Okay, so this is the concept of regular graphs. And now, consider this problem. So now the task is one. I will give you a number of vertices, say n, and now try to construct a graph on n vertices such that every degree of this graph will be different. Every vertex will have this degree. So you can try. What do you think? Is it possible or no? It's no result, yeah? Is it possible? Do you think that yes? Perhaps no for some combinations? So the question is whether we can construct completely irregular graph. Okay, so such a graph that every vertex will have this degree. So it is something like from the basic course of graph theory, it is possible, it is not possible to do it. So let me show how we can prove it. Okay, so if we have a simple graph, so when we do not allow multiple edges as roots, then trivially every vertex has degree at least 0 and at most n-1. So what does it mean? If you like to construct a graph such that every vertex must have distinct degrees. So then the degrees of these vertices must be distinct numbers, either from set 1, 2, 3 up to the n-1, yeah, or from the set 0, 1, 2 up to the n-2. Can you see why we cannot have here n-1? We have a vertex of degree 0, so it is not connected to any other vertex. So the maximal, maximal degree of n-2. Okay, and now, what is the cardinality of this set? n-1. But how many vertices we have? We have n vertices. Okay, so it is not possible to construct a graph that is complete, simple graph that is completely irregular. Okay, so for simple graphs, it is not possible to do it. However, when we allow parallel edges, we will deal with multigraphs, then such graphs can display this property. Okay, and this problem was proposed by Charles Frank, Jacobson, Leo, Olerman, Saba in 1998, and they asked the following. So consider loopless multigraph. So we allow parallel edges, but we do not allow loops. And now we ask, determine the fewest parallel edges required to ensure that you obtain a graph or multigraph with all vertices having distinct degrees. Okay, so let's consider this example. Yeah, here we have a graph. We know that it is not possible to get distinct degrees for all vertices when we do not allow parallel edges. So, for example, this vertex has degree 3. Here, this vertex has degree 3. We have here another vertex of degree 3, another vertex of degree 3. This vertex has degree 4, this vertex has degree 4. So we have to add some parallel edges. You can try to do it alone, or I will show you some solution. Okay? So we have this one. Okay, so now we added several edges, several parallel edges, and now we will check what are the degrees of the vertices in this multigraph. Okay, so for this vertex, now the degree is 5. Yeah, for this vertex is 7. So we see that every vertex has distinct degree. And now, somehow we are lazy. We do not want to draw parallel edges. So what we will do? We will construct the corresponding label graph in the following way. Look, here, between these two vertices, in a multigraph, we have two parallel edges. So what we will do, in the corresponding label graph, we will assign number 2 this edge. Here, the edge between these two vertices as number 3. So what does it mean? That in the corresponding multigraph, we have 3 parallel edges. Yes? And now, here, the degree of a vertex corresponds in the multigraph corresponds to the weight of a vertex in the label graph. So we have a connection, one-to-one connection between the multigraph and the label graph. Okay? And this leads to the concept of irregular assignment. Okay, so what is irregular assignment of graph? So it is some mapping that assigns numbers 1, 2, 3 up to some number k to the edges of a graph, such that we require that all vertex weights are pairwise listed. Here we have a definition how the weight of vertex is defined. So weight of vertex V is defined as sum of all edges of all labels of edges adjacent to the vertex. So check this definition and tell me whether it is similar to some other definition. We have a very similar definition. Just one condition is now shared. This is almost like anti-magic labeling, but just here what we do, we can repeat numbers. Okay, so when we require that the edge labels are distinct, we have anti-magic labeling. When we allow repetition of labels for the edges, we get irregular assignment. Okay. This definition was defined by, as I said, Chatra and Jacobson, Ollerman, Lewis, and Saba. It's quite an old concept, and a lot of is known about it. Okay, so let's try to find irregular assignment for this cycle. So my first question is, what is the smallest possible vertex weight for this cycle? 2. How we can get 2? Every vertex is irregular, so 2 vertices contribute to the vertex weight. And the smallest label that we can use is 2. Okay, so we assign number 2, it's better said, we assign number 1 to these edges, and we get weight 2. And then we need to get another weight. Cannot repeat weights. So the next possible weight is 3. So let's assign number 2 to this edge. We will get 3. Next possible weight is 4. So let's make 4. How? 2 and 2 is 4. Next one is 5. How we can get 5? For example, 3 plus 2. Then the next possible, smallest possible weight is 6. 6 is a sum of 3 plus 3. Next one is 7. 4 plus 3. And now the next possible weight is 8. But look, if we would like to have 8 here, what does it mean? What must be the label of this edge? 4. But what will happen here? 5. It is not belong. So 8 is not good. So what else can be here? 8 is not good. Can we get 9, weight 9 here? So if you would like to have the weight 9, then it means that this edge label must be 5, but yeah, that's a problem. So what do you think is the smallest possible? 12? Yeah, when we give here 7, when we give here label 7, then we get the situation that all vertices of at least distinct. Oh, I can say that it's for the weight of every vertex is. Okay, but you can see it's not optimal. Yeah. So what does it mean, optimal? So what we would like to optimize? How? What might be? How effective it might be? What would you like to do?
Use minimum value.
Yes, you would like to find the minimum edge label. Okay? And this minimal edge label is called the irregularity standard of graph G. Okay, so let's think about this graph. Okay? We have cycle on how many? On 8 vertices. So how many edges we have here? 8 edges. Yes. So we know that the minimal vertex weight is 2. Yeah. So it is 2. So what is the minimum for the maximal vertex weight? The weights must be distinct, so it will be optimal if we will have weights 3, 4, 5, 6, 7, 8, and 9. Yeah, because we need to have 8 distinct weights of vertices. And now we would like to get labeling with vertex weight 9. This graph is irregular. So how we can get 9 as a sum of 2 integers? 4 plus 5. Yes. So we have the lower bound for the irregularity thread of this cycle. It's 5. It cannot be less. Yeah, because this is the maximal vertex weight must be at least 9, and 9 must be the sum of 2 integers. So we have that the maximal label must be at least 5. Okay, so now try to find such labeling for this graph. So we can do it, for example, in this way. Yes, so we have B label 1, 1, as in the previous case, and now 3, it's 1 plus 2. But now we will not go in this direction, but we will go to the opposite direction. Yeah, so we will assign number 3 to this, the edge is 4. Then we will skip on the next side. 3 plus 2 is 5. Then from the other side, we get 26. Then 7 is a sum of 3 plus 4. And when we assign number 5 here, we are done because we see that all vertex weights are distant. Okay? So is it clear how we obtain it? Okay. So we know that the irregularity state of graph is minimum k for which the graph has irregular assignment using maximal edge label k. Okay, and now this parameter is finite if and only if the graph contains at most 1 isolated vertex and no isolated edges. Why? So again, if we have isolated edge, then the weights of the endpoints of this edge must be the same. We can do nothing with that. Okay, what happens when we have isolated vertex? So what is the weight of this vertex? So 0. So we can have only at most 1. For the other graphs, the parameter is finite. So it is non-result. Okay. So now we will try to find some terms for this parameter. So we know that the vertex weight is defined as a sum of the labels of all edges incident to the given vertex. Trivially, we know that the lower bound for the vertex weight is minimum degree of graph, because what we will do, we will check the vertex degree and we assign all adjacent edges, incident edges with number 1, and we get the minimum for the vertex. And now, how we get the minimum for the maximal vertex weight? It's the same as we had here. Yeah, we know what is the minimal weight. It must be at least minimum degree of the graph, and then we have to get distinct degrees, distinct weight. And so sometimes I will say the word degree or weight, but I think the same. Okay, so how many vertices we have? Say region, yeah? So we have delta G plus 1, delta G plus 2, and so on. And the minimum, yeah, for the maximal vertex base, it must be at least minimum degree of graph plus number of vertices in the graph minus. So this is trivial over bound. But the maximal vertex weight we can get only such that we will use the maximum when we know that all labels edges are at most k. So we have the upper bound for this parameter, yeah, for this vertex weight, because we have delta G, yes, maximal degree of graph G, and every edge is labeled by the maximum possible label. So we have this upper bound for this parameter. So combining these two, we get some lower bound for the irregularity state of the graph. Yeah? It's the ceiling of the number of vertices plus minimum degree minus 1, the whole divided by maximum degree. Yeah, it must be integer, so we have this one. Okay. Of course, there are now some other lower bounds. So let me speak a little bit about this one. So let and I denotes the number of vertices of degree I. So consider that we have in our graph we have 3 vertices of degree 4. So we have that the minimum weight of all of these vertices must be at least 4. Yeah, because we assign number 1 to every edge. So it is 4. But these vertices, they must have distinct weights. So this is 5, at least 5, this must be at least 6. So we have number of vertices of degree I plus, yeah, the weight of this vertex is at least I, yeah, because this is the degree of this vertex, plus number of vertices minus 1. And it is realized, this sum, as a sum of I integers. So we divide it by I. And again, we have to take a silly one. Of course, we have to get through all possible degrees in the graph. So we have this one. Okay. Is it clear, Tita, or do you need more explanation? When we consider regular graphs, so we know that regular graphs is all vertices of the same degree, say R, then immediately from this one, we obtain that the irregularity state of this graph must be at least number of vertices plus R minus 1 all divided by R. Okay. Let me now tell you some results about this graph invariant. This is how to say. To find the irregularity state of graph is a very complicated problem. So in general, we have some bounds. So let me show you now some results. So it was proved by Andrea and Fish that if we have a graph with at least 4 vertices, so we exclude the graphs that contain isolated vertices and isolated edges. So it means that we exclude the graphs that have infinite irregularity state. Yes, so they are not existing for that anymore. And now they prove that irregularity state is valid from above by number of vertices plus 1. Later, Podri, Jacob, and Wells, they prove that irregularity state is at most 3 if the minimum degree of a graph is at most number of vertices minus some integer t, where t is at least 1, and at most square the root of the number of vertices divided by 8. Yeah. Later, Jakub Šibiło, we prove that the upper bound for this parameter it is 112 times of number of vertices divided by minimum degree plus 28. Okay? And the best bound of this type was proved by Kalkowski, Karonsky, and Fender, and they obtained this result. Yeah? So we have general upper bound for the graph. Yeah? It is 6 times number of vertices divided by minimum degree plus 6. Okay? This is the best bound of this form for the irregularity state of graph. Of course, for some graphs, you can the exact value of this parameter is smaller. So let's think a little bit about this one. Here we have some what is not. Yes, so when you are interested, you can find many results. Okay, so let's now deal with irregularity state for some standard graphs. We know it was true that if we consider a path on at least 3 vertices, then the irregularity state of this path depends on number of vertices. If number of vertices is congruent 3 modulo 4, then irregular straight is equals to ceiling of n by d. Yeah. And in other cases, it is number plus 1. So let's try to find irregular assignment with corresponding number or with corresponding irregular straight. Would you like to try, or shall I show you? Immediately show you. You are tired. Okay. Okay. So we can do it. This is a very simple construction. 1, 1, 2, 3, 4, 4. We have how many vertices we have here? 1, 2, 3, 4, 5, 6, 7. Okay. So using this result, we get that 7 is congruent 3 modulo 4. So it must be 7 by 2, and so like that. So it must be 4. The construction is like that. So we can check the vertex weights, and we see that they are consecutive numbers. They are these numbers. 1, 2, 4, 3, 4, 5, 7, 8. So it's the other. Yeah. So this result. Okay. So let's check what is known on cycles. So again, here for cycles, we have to distinguish again 2 cases. If the number of vertices is congruent 1 modulo 4, then it's n by 2, and this is that. In all other cases, we have to increase by 1. And again, for illustration, we have a cycle of 6 vertices. 6 is congruent 2 modulo 4. So we get that the irregular straight of the graph will be 6 by 3 plus 1. 6 by 2 is 3. By 1 is plus 1 is 4. Yeah. So we have this labeling. And when we check the weights, so we see that they are all reduced. Okay, so there are lots of, usually, if you don't have more time, you should try to do it alone. Maybe it will be more valuable for you when you will try to find the labels alone, because then you will somehow feeling how to do it. But now just I will show you. Later when you will have the yes, please. It's the result. So they prove it. Yeah. So it is result proof. I don't remember who proved it, but we just follow that we know it, that somebody proved it. Sorry? Yes, we had the lower bound. Yes, so we know that the minimum weight must be 1. Yeah, and then you count, minimum weight must be 2, like 1 plus 1. And then you count how many you have, what is the optimal sequence of weights. And then you get the minimum for the maximal weight, you divide it by 2. And so, and you will get something like that. So you, in general, you have to distinguish 4 cases. And for some cases, you know, you get exactly the lower bound. For some cases, if you are interested, we can try to do it. If not, we can go through the other list. So it's
I think this paper is published.
yes, of course. Yeah. I just like to show you some results and to show you labeling parameters. Another question? So please ask if you have another question. Okay, and now I will tell you something about another type of irregular labeling, irregular assignment. Okay, so Ali Ahmad, Al-Mushad, and Martin Bacha, they defined a new irregular label such that, you know, in previous case, we labeled what? We labeled edges, and then there is a typo because now it should be very, sorry, I was doing it early in the morning and I was very sleepy. When I will send you this this talk, this presentation, I hope that I will change I will forget on it. So they changed the domain. Yeah, look. Sorry, I just copied it and I didn't change it. Okay, so here this edge set should be that Vertex set. Okay, so what we do? Now, we assign numbers from one up to k just to the vertices of the graph. And we will check the weights of edges, yes, because it's edge irregular. So we have to check the weights of the edges. And we require that every edge will have distinct weight. Edge weight is defined as the sum of the labels of the edges. And again, our goal is to minimize the maximal used label. In this case, Vertex label. And this parameter is called edge irregularity of the graph. So let's have an example. We have again our path, and we assign numbers to the vertices. So at least the picture is correct. Sorry. I hope that I will not forget to change it. Okay. So we assign, you can see that again, the labeling for this structure is very, yeah, you send 1, 1, 2, 2, 3, 3, and then 4, 4, and so on. There is something else. Okay. So we can check the weights of the edges. Yes, for example, for this edge, it is 1 plus 1 is 2. For this edge, it is 3 because it is 1 plus 2, and so on. So, it's very simple. Of course, it's a simple graph. But what we have a little bit more complicated structure. Say, for example, complete bipartite graph. Something that looks very nice. It's a regular graph with a structure. Yeah. So here it is much more complicated because what we have. Yeah, we have a lot of edges. And so we have to somehow guarantee that the weights of edges will be distinct. Okay. And consider that if you have complete graph, the situation is much more complicated. Yes, because what you have, say that you have 6 vertices. And I think something is missing. Yeah, and you have to join everything instead. And now it's a problem. It's not so easy to find. So there are several ways how we can do it. To prove that it was obtained by, I think that it was proved by Ali Ahmad. I think that many of you know him. It is his proof that they were using. For labeling of vertices, they use Fibonacci numbers. Yes, because if you use Fibonacci number, so you can guarantee that the sum of 2 Fibonacci numbers, sum of any 2 members of Fibonacci sequences, if the Fibonacci sequence has some nice property, that you will get the resulting sums to be different. Yeah, so this is one way how you can do it. Or another way how you can do it is, and something that gives a much more better bound, is to use Sidon sequence, for example, yeah, or some other sequences with some nice properties. But I'm not sure, but I think that for complete graphs, this problem is not solved. Yeah, the exact value. It's complicated, because you can find some construction for general, for some small, for some small values of n, if you have complete graph on n vertices. Somehow you can show that it's not possible. Yeah, but if you have too many vertices, how you show that your bound is the best. So you will get some upper bound. So this is also, it seems very easy, this problem, especially when you start with the path. Okay? But for a general graph, it's complicated. Okay, so let's check some bounds of this parameter. Okay, so what is the lower bound for this irregular district, for this graph invariant? So it is the maximum of this fraction and maximal degree of the graph. Let me discuss a little bit more about these 2 members of this set. Okay, why we have this? So if we have a graph, any graph, what is the minimum weight of any edge? It's 2. Yes. 1, 1. In such a way we can get 2. So as we would like to have the distinct edge weights, so the next one has been at least 3. Yeah, the optimal set of edge weights is 3, 4, 5, and so on, up to the 2 plus number of edges in a graph minus 1. Yeah, so it is exactly number of edges plus 1. Yeah. And the sum, edge weight, is obtained as a sum of 2 numbers because of the edge has 2 endpoints. So we have this one, and of course, both these numbers must be integers. So this is trivial. But consider that we have a graph with a degree, with a vertex is a very big degree. Yeah. So for example, using this condition, we get some bound. But for this case, it will not work because this central vertex C, its label contributes to the weight of every other vertex. Yeah. So the minimum weight for this edge is 2. Yeah, and we will get it such that we will give here 1 and here 1. And then, if you would like to have here 3, so the only way how to do it is to increase the vertex label. Yeah, so it must be 2. Then, if you like to get here 4, so we cannot change the label of the central vertex. So we have this one is 3, and so on, yes, up to the maximum degree of the graph. Yes, and there are graphs, yes, this bound is stacked. There are graphs that have their irregular set exactly this fraction. Yeah, for example, we have the results from passes. So irregular set of pass is exactly this fraction is number of vertices divided by 2, and the silicon y, because number of edges in the graph is number of vertices. Minus 1 plus 1, and we have this. Okay?
Should be yes, right?
Sorry?
Should be yes, yeah.
Oh, yeah. Again, typo. Thank you. So, and there will be another. Sorry, I did my thought. This part I did. I hope that on the other slides you will not find typo like that. So for you, information, don't do slides when you are sleeping. So this is something that is like message for you from all my notes. Okay, so when you are sleeping, better go to the bed. Okay, so again, typo. Okay, so we have a star on n plus 1 vertices. So we have a vertex with degree n, and trivially the irregular set of this graph must be n. So please, I will send you slide, but I will not change the typos. Please send me a quick email and I will update it. Okay. Okay. So this is the result. Okay. And now we do not have a lot of time to cover all of these varieties of irregular assignments, but I would like to show you some of them. Okay, so here I will go through different types of irregular assignments, and one time the time will be over, I will stop, but you will find it there. And I heard that you will have some talk you on next week. Some of the people who are here, they will present their results, so you will get more information about some different kinds of labels. So when I will be on your topics, please tell me that, okay, I will tell you more about it. Okay, So now let's discuss vertex irregular total K labeling. So what does it mean? How you can read it? What do you know? What you can say about this type of assignment? Total, what does it mean total? For the label, vertices and edges. And so we extend the domain and we label vertices and edges. Then vertex irregular. What does it mean vertex? So we check the weight of vertices. Irregular, it means that they are this way. And K labeling means that maximal used label is K. So now you are expert in terminology. So when you will read some papers, you will be able to follow. Because at the beginning when you start to read something, you have to understand terminology and the definition. So now you will be able to read. Okay. So here we have a definition. So we assign numbers from 1 up to K to every vertex to every edge of the graph. And we will check what are the weights of the vertices. We require that the set of all vertex weights consists of these two numbers. And here we have a definition of the vertex weight. Yeah, under the total group. But so it's not complicated. Okay. And the corresponding graph invariant and the minimal K for this labeling is called total vertex irregularity strength of the graph. And it's a shortcut is TVS or G. Okay. So here we have example. Okay, so we have a cycle. We assign numbers to the vertices, edges of the graph, and we will check what are the weights of vertices. Yes, because we have vertex irregular graph. So, for example, for this vertex, it is with 1 plus 1, the labels of the incident edges plus the label of the vertex itself. And we will do it for all the other vertices. And again, you can find many results, some bounds on this graph invariant. You can find the work of Martin Bachastanoye and Ron Ryan. As you can see, the names always repeating. So when you want to start to work on labelings, then you will get so you will try to solve many problems in different areas. Okay, so these bounds were improved by Jakub Szybilo and the other boys from Poland. And if you are interested, again, you can find many surveys and many results. Okay, now, any questions to this type of labeling? Now I will introduce you just different types of labeling. Okay, so yeah, H irregular total K label. So what does it mean? Total label. Okay, it's another type of irregular assignment. Total means that we assign numbers to vertices, edges of the graph, and we will check the H irregular. So we would like to get such situation that every edge will have this effect. And we try to minimize the maximum possibility. Okay, so here is the definition. Just let me recall that the weight of H is then the sum of the labels of n vertices plus the label of H inside. And we have again this total H irregular strength. Okay, so we have this one. Again, example. So we have a graph, we assign numbers to vertices on the edges of a graph, and we will check what are the weights of the edges. For example, this edge, it is 1 plus 3, the sum of the vertices, it's 4, and the label of the edge is 3. Okay, so we have this type of labeling. And again, for lower to be done, we have some lower upper bound for this invariant. And again, we have a very, very nice conjecture by Ivanchov. And this conjecture is saying that total edge irregular spread any graph is the maximum of the following two numbers. Yes, so the number of edges plus 2 divided by 3. Yeah. Again, the minimum weight for an edge is 1. Is 3 because 1 for vertices plus 1 for edge. So it is 3. And then every edge must have this weight. So we have 3 plus number of edges minus 1, these elements in an optimal sequence of values. And then as the vertex, as the edge weight is the sum of the elements, we will divide by 3, and these numbers must be integers, so the variables. Okay. The second part is again from this concept. We have a vertex with a very, very large maximum degree. So one parameter that comes into the sum is fixed. So when we would like to distinguish the weights of the edges, we can play just with the edge label and the label of the second vertex. Yeah. And it is really, really nice conjecture. Again, it's open, maybe you will find it. Of course, for some families of graphs, we could prove, yeah, for example, for complete graphs, complete by matrix. And you can see, for example, the last one, it's a result for large dense graphs. Yeah, we have a lot of vertices and a lot of edges, then we have this result. Okay, so it's another way, maybe where you can start over. Of course, but maybe you will come with some new ideas and you will be able to solve it. Okay, another variation. So, last topic was that we check the weights of edges. But how we can generalize this concept? What is edge? So edge is nothing else than K2. Yeah. So what we do? We have a graph and we check the weight of every subgraph in our graph that is isomorphic to K2. We can generalize this concept. Why to restrict only on K2s? Choose any graph. For example, if we have this graph, yeah, so what are the possibilities? We can check K2. So it is a possible concept. But here we have also cycle C3. We have here also cycle C4. And so on, yeah. Or other structures. K1, 3, we can cover by stars. And we can check the weights of the subgraph. Okay, so this is another extension or like a generalization of this problem. Okay, so here we have to define some new terminology. So we say that graph G has H covering if there exists some family of some subgraphs, say all of them are isomorphic to some given subgraph H. We have P such subgraphs, and we require that every edge in the given graph belongs to at least one such subgraph. Like for this graph, this wheel, it has covering with K2, C3, C4, K1, 3, but it has no covering with K1, 4, for example. Yeah? Because we can cover only these edges, but not the edges on this outer cycle. So what we do, we consider we have a graph and we require that this graph has edge covering. And now what we will do? We will now check the weights of all subgraphs isomorphic to the given graph. Yeah? And we require that these weights are all these. So if we restrict only on H will be K2, so we have the concept of H irregular labeling, either total or not. Yeah. So what we are doing, we assign numbers from 1 up to K, and we have a total labeling to the vertices and edges of a graph, and we will check the weights of the subgraphs isomorphic to the given graph H. Okay. And the corresponding graph invariant is called total H irregular stage of the given graph. Yeah, we can try to minimize the given graph. Okay, so as I told you, if graph H is just K2, it's something that we already know. It's a known concept called as H irregular total H labeling. So let me explain. Some example and show you something. So here we have a site, we have a path, this graph is called path. So we have a path, we add one extra belt, we add one extra vertex, and join this extra vertex to all other vertices of the path. And now we would like to find labeling such that, for example, every cycle 3 will have distinct weights, 4 and so on. Yeah. So in the case, when we will check the weights of all cycles C3, it's easy to see that every edge is covered by some cycle C3. Yeah, can you see? I will show you. Yeah. So consider we have this type of labeling. And now we will check what are the weights of the cycle C3. So the first one is 6, then 7, 8, 9, 10, 11. Yeah. Or we can ask what in the case when we will have cycle C4. So again, we have a labeling, and now we will check the weights of cycle C4. So the first one is this one. Yeah. So this one has weight 8. Why 8? We have 4 vertices, 4 edges, so the minimum is 8. And then we try to construct such labeling that we get in an optimal way, we will get weights that are consecutive. Yeah, so 9, the next C4 is 10, 11, 12, and so on. Okay, so we have some bounds. We can prove some general bounds for any graph for this parameter. And so we can prove that this exists. Okay.
So,
yeah.
There's some graphs H don't have any labelings.
It depends whether you have like for the total labeling, we have like we can prove that this exists or you can always find it. Yes, you just try to minimize it. Yeah. If the graph is like that, of course, the necessary condition is that the graph has to have H covering. And if it has, then you can you have a construction that we are able to prove that it is always possible to do it. Then you just try to minimize it. Yeah, there are not some bounds for that. So it's like, give me a graph, it's covering, and I will find it. Yeah, of course, there are 2 ways. You have to show that something like that exists, and then you try to minimize it. Yeah, so in general, you need to, or do you need? You would like to have, bound. Yeah, so it's something like that. Okay. Of course, there is Vertex version of such labeling. So we have a situation that we label on the vertices of a graph, yeah, and the corresponding invariant, edge version of this problem. Yeah. Please now don't ask me about bounds because I don't remember. But if you are interested, I can tell you where you can find it. Yeah, so, but for some cases it does not exist. But I don't remember now. But if you are interested, I can tell you. Okay, and now I have a few minutes, but don't worry, because another extension is regular reflexive labeling. And on Monday, you will have on Monday, yes, I will tell you some results about this labeling. So I will finish, I have only 2 minutes, but that's great because I will introduce you only the definition. Okay, so what does it mean that we have a reflexive labeling? So you remember at the beginning we have the degree problem. From the degree problem, we obtained labeling. And Joe Ryan, Munasiga, and Dushan Tana, they had a nice idea. Again, come back to the degree problem and to ask for the following. Yeah? They combined total labeling problem, so we assign numbers to the edges and also vertices. Yeah, we know that for the degree problem, the label of the edge was corresponding to the number of parallel edges. And now, somehow, we need to associate the vertex label with something. What it will be? So the vertex label will somehow represent loops. But what does it mean? Yeah. So this association or this property has the following effect. Yeah? Every vertex label must be in. Why? Because when we have a loop, so every loop contributes twice to the degree of a vertex. Yeah. So this is the first condition. And the second one is that we allow to use number 0 for vertices. What does it mean? That the corresponding vertex does not have a loop. Yeah. So there is no loop. Okay. So let me show you just example and then I will stop. Okay, so we have again a cycle and now we construct, yeah, we would like to get completely irregular now pseudogram. Yes, because we allow not only parallel edges but also loops. So one way how you can do it is do it this way. It's in fast switch. So we have this now. Yeah. And how we will get the corresponding labeling. Okay, so let's have a look. For example, this vertex, yes. So here we have one loop. So it means that we assign number 2 to this vertex. 3 here means, of course, that between the corresponding vertices in the pseudograph we have 3 parallel edges. Yes, here we have for this vertex it has label 0. So it means that between the corresponding pseudographs, there is no loop. Here we have number 4, so that it means that we have 2 loops. Okay, so and I will stop now. You will get more information next week. Just I will show you, yes, what everything is you can find here. Some connections, then you can read it, and you will be interesting, so you can find some information here. Because I would like to show you some else distance irregular labeling, and you will have more information with another talk. Okay, so many variations. So if you are interested, so this is just like a very brief survey of different types. So when you are interested, you can find many information here. Yes, so some concepts. And I would like to go to the end. Yeah, that's it. So thank you for your attention. I'm very happy that